Alrighty, folks. So let's start with the truck route. A delivery truck travels 16 blocks south, then 9 blocks west, and 7 blocks north. Assume the blocks are equal length. They're asking us to find the distance the truck has traveled, the magnitude of the displacement, and the direction of the displacement from the origin. And they are asking for that in south of west. So gives us a little direction out there. What I'm going to use for the type of sheet on this one, I'm going to use the vector diagram one, so that I think that's the best Y for this. Would be a vector diagram. So I'm going to plot out vectorially the route that my truck has taken. So 16 blocks south. We're going to start right about here. And stage one, let's see, one. Say 1, 2, 3, 4, 5, yeah. I'm going to call that 16. Then 9 blocks west. So about that far west. This, of course, being north, right? And then 7 blocks north. So that's my route, right? And part A asked me for the distance, and this is where in the Y, I could also make sure that I explain that I understand what distance is. Distance being the length that you have traveled, right? Back to our kind of beginning of September. Remember, we're going back through all the same topics. So distance is how far you have traveled. Well, how far I've traveled is 16 blocks plus 9 blocks plus 7 blocks. So 32 blocks. So that should be part A. Okay, let me try. See if it works. Oh, it's not like in the units. Where it put in the units. Interesting. Where it submitted the units. Well, the value. All right, so let's go on to part B here. The magnitude of the displacement of the truck from the origin. So now what we're looking at for part B is we're looking at this vector here, delta D, which would be the displacement, and the magnitude is the length of that vector, and then the directionality is part C, where they asked us south of west, I think, was it? Is it south of west? So I'm going to redraw that vector just to make it easier for me to see. Let me scroll. There we go. And this is the same blue vector. It's going to have components, a east-west component and a north-south component. The east-west component is going to be 9. I can get that by just seeing it's going to be the same width as my only westerly movement. The north-south component is going to be my 16 minus 7, which in my case is also 9. Oh, for me, it's nice. It's a 45, 45, 90 triangle. May not be for you, so I'll act as if I don't know that. And so that, because for yours it probably isn't. So what I'm looking for is the length of the blue and what angle it is south of west. And so I'm going to use Pythagoras, a squared plus b squared plus c squared, equals c squared, from the back of our equation sheet. So I have 9 squared plus 9 squared, and this I could put blocks in here, equals delta d quantity squared. And for delta d, I'm going to end up with, let's see, with 9 squared plus 9 squared I get 12.7 blocks. And you're saying that one wasn't going in either, right? Okay. I will check on that one, but that's the correct method for it. And then to figure out theta, now, how many things are there to know about a triangle? Just in general. Hello? Anyone out there? How many things to know about triangle in general? 6. Okay. 3 angles and 3 sides. Right? As long as you know 3 things, and at least one of them's an angle, at least one of them's a side, you can find everything else, no matter what the triangle is. 3 things, 1 an angle, 1 a side. So we actually know, well, let's see. We know 4 things about this triangle. We know all 3 sides. We know one of the angles is a right angle. So we know that we can find everything else. What number are we least confident about? The 12.7, because that one we calculated. Maybe we screwed up. Maybe our calculator was on the fritz. But I'm pretty confident in the 9, the 9, and the right angle. So I'm going to use those to find my theta. That way, even if I messed up in step B, I'm not going to hurt myself in step C. And so I look at theta and I say, well, I know the opposite side of it, and I know the adjacent side, and I know it's a right triangle, so I can use SOHCAHTOA. And the one in SOHCAHTOA that relates opposite side to adjacent side is TOE. So the tan of theta is the opposite, 9, over the adjacent 9. So that means, now do you guys use inverse tan or arctan? Which, arctan? That's the, okay. They mean the same thing, you guys know, right? It's just 2 words, it's 2 words for the exact same thing. Inverse tan or arctan. No, the inverse function of tan. But inverse tan is same as arctan. It depends upon who your teacher is, really. So arctan of both sides gives me arctan of 9 over 9 equals theta. And theta will equal 45.0 degrees in my case. All right. All right, 3.26. So vector A has a magnitude of 27 meters and points in the direction of 32 above the positive x-axis. Vector B has a magnitude of 35 meters and points in a direction 55 degrees below the positive x-axis. Use the component method of vector addition to find the magnitude of vector C. So we're adding those 2 to get C. Well, I'm assuming they're saying A plus B equals C. It'd be nice if they actually said that, but using the Bohm method, find the direction of C. All right. So, and that's degrees below the positive x-axis. All right. So let's draw these. And so we're going to use our vector sheet again. And 3.26. All right. $27 meters and points in the direction 32 above the positive x. So this is my vector A. And then 27 and 32. So this angle here is 32 degrees. And this is 27 meters, right? And then B, 35 meters and points 55. So B is going to be in this direction. This is 55. And this is 35. All right. So those are my two vectors. They're asking me to use tip to tail. So what I'm going to first do is find the components of each of those. I could do them tip to tail. I'd end up with a non-right triangle. And that would be okay if you knew how to deal with non-right triangles. But I'm going to assume that you guys don't know much about non-right triangles. Is that a good assumption? You don't know much law of sines, law of cosines? Okay. So I would always fall back to the right triangle ideas. And so I'm going to do the components here. And I'm going to mix up my colors a little bit just so you can see them better. And my components here. So the adjacent side is always the hypotenuse cosine of the angle. The opposite side is always hypotenuse sine of the angle, based on SOHCAHTOA again. SOHCAHTOA and Pythagoras are your friends. Make friends with them. So this side here would be 35 meters cosine 55 degrees. Remember, those working on the computers, you have this in front of you if it's hard to see up here. You can pull up the window. And then this side would be 35 meters sine 55 degrees. On A, the adjacent side would be 27 meters cosine 32 degrees, and the opposite side would be 27 meters sine 32 degrees. Good? No? Yes? So now, if I'm adding these vectors together, I can add up the parts, and that's the same as adding up the whole. All right? Think about if you've got bags of things. If you add the two bags, and you want to find the total mass, you mass the two bags. That's the same as if you take everything out of the bags and mass the individual parts separately. It'll add up to the same amount. So the x's, I'm going to add the x directions. I'm going to add to the x's, the y's. I'm going to add to the y's. Sorry, that would have been good to put up here in the corner, right? X and y. So let's add up my x's. I'm going to have put them tip to tail. Actually, move those down here. So those two add like that. And then my y's, I'm going to take a guess just because they said what angle to the negative to the, in their answer, and this is just, they said angle below the x positive axis. So I'm thinking they set up the problem that B has a larger vertical component than A, right? And if I did the math right now, I'd find that. So I'm going to range up. There's my A, and then my B, I think, is going to end up being in that direction. So I've arranged my components tip to tail. So that means that they all add up to the resultant of adding all four is from the tail of the first one to the head of the last one. So I've arranged them all tail to head, and then my last one goes like that. It's going to have components that line up with it. Actually, I'm going to hold off on drawing the, hold on. I want to draw them just a little bit different so we don't. So that's going to be my result. My result, it's going to have an x component that lines up here and a y component that lines up there. All right. The red one would be vector C. Yeah. Right. So now I'm going to call this vector, that length CX, and this one, let's call that CY. And now the math is almost done. Well, it's laid out nicely now. So if I want to find out the value of CX, that's going to be 27 meters cosine 32 degrees plus 35 meters cosine 55 degrees. And they're both positive. So they point, and they both point in the same direction. I can figure out my value for CX. Then I can figure out my value for CY. That's going to be positive 27 meters sine 32 degrees minus, because it points downwards, 35 meters sine 55 degrees. And I'm expecting a negative answer with CY. I'm expecting it ends up pointing downwards. So I expect a negative answer here. And now I have it, so that, those two, so then I can do CX squared plus CY squared equals C squared, and C is what they're looking for answer A, part A. Right? So they want the magnitude of it. And then for part B, they want to know the angle of this below this axis. So they want to know the angle theta here. And again, I have the adjacent and I have the opposite. It's a right triangle. So I'm going to again do the tan of theta is opposite CY over adjacent CX. And those are lengths, not vectors. So don't put in the negative for CY. It's the length of that side. So it's just a positive value. So of course theta therefore equals the arctan, again, of CY over CX. And you solve for theta. And it should be degrees, and it should be below that axis. If you don't get a negative value for C sub Y, then you're above the axis, and you need to think how many degrees would it take to get from that axis going clockwise all the way around to my other one. But my guess is they set up the values so that it would work out. Any anything on this one you want me to go through again, or questions or things like that? All right, so we're going to do 4.27. As I just said, a lot of vector diagrams in this one. I don't think the math is any trickier than what we just did in the last one, but getting these arranged the correct way so that you can see them can be a little tricky. Remember that whenever we have addition, we're lining them up head to tail. When we have subtraction, that negative, think about what negative means. How is 3 different from negative 3? Opposite directions. Whenever you see like minus b, that means it's the same length as b, but in the complete opposite direction. So you flip it around. So let's do the vector diagrams for each of these. And then if needed, we'll do the math. But all the math is Sokoto and Sagers, and I think you guys can probably do those. So we've got vector A, positive y direction, 12 meters. So vector A, positive, and that's 12 meters. That's vector A. Then we have vector B, 33 meters, negative x. This is B, and it's 33 meters. Those aren't perfectly to scale, right? But they're pretty good. So the first one they want A plus B. We're going to list all these out so that I have them. They want A plus B, A plus B, A minus B. So let's scroll down a little bit. Extend the page even. Yeah. And here we'll do A minus B. Then they want B minus A. And okay, those are our 3 arrangements. So let's draw A plus B. So I have A, and then B. And the resultant of those would be in that direction. So that would be C. What's that? The other way to think of A minus B is A plus negative B. All right? So if I have A, I'm going to add to it the opposite B, but in the opposite direction. So I'm going to take A, and now I'm going to have B that doesn't point in the negative x direction, but points in the positive x direction. And I get a C. That triangle look a little similar to the previous triangle? Yeah, it's just a different orientation, right? But they're similar triangles. Yes? Okay. And then B minus A, and the other way to write that, of course, is B plus a negative A. So now my B is back pointing to the left. but my A points down now. So I'm going to have A plus positive B, points in that direction, giving me my resultant C in that direction. So my directionality changes in each one of these, but my magnitude doesn't. Yes, no? Should be, yep. Because you have similar triangles. You've just, almost in a sense, rotated the triangle around or flipped it around. Yeah. Good. Do we need to do any of the math? I mean, the numerical math. We kind of did math here by doing the drawing. All right. Good. Let's, all right. So we got spaceship traveling to deep space towards the space station. Need to make a course correction to go around the nebula. Or the ship to travel 23 kilometers before turning at 70 degrees and traveling 23.5. So it looks like the length of A here, 23 kilometers. Theta in the diagram they gave us is 70 degrees. And then it travels another 23.5 kilometers. Before assuming the path was the captain not order the course correction, what it would have been the magnitude of the path the spaceship traveled through the nebula. So they're asking us to combine these two vectors and find the resultant. All right. So I'm going to grab the picture just so, no, I'll redraw it. A, B, J, okay. So let's, another vector sheet. There we go. That's locked. Okay. So we went this way as A, and then up this way as B, and they want to know the resultant C. Now, when I look at this, I see a non-right triangle. How can I make it a right triangle? Any ideas? How do I make that a right triangle? Well, if I do the components of B here, I can make it into a big right triangle. And I know that this angle in here is 70 degrees. So that means the adjacent component is B cosine 70 degrees. And the opposite component is B sine 70 degrees. And now I have a big right triangle, where one side is the length of A plus B cosine 70. The length of the other side is just B times cosine 70. The hypotenuse is my displacement. And they're asking for the angle down here. I believe, let's make sure. Displacement. And what would be the direction of path spaceship if it had traveled through the nebula? So yeah, they want to know what angle is there. But seeing that you can add the components there and have a big right triangle is kind of key to being able to understand this one. Whenever you can, make components and see if it makes your life easier. Yeah. Yes, so the magnitude of this side here, this whole thing, would be A plus B cosine 70 degrees. And that would be one leg of the triangle, and the other one is B sine 70 degrees. I'm gonna pause here so I can save these notes. All right, please do the exit ticket. You have 4 minutes or so to be exactly in time. And I will check on that one that's malfunctioning.